This is lesson 3 where we compare the difference between heat and temperature. So hopefully you just got done doing the exercise where we were heating these two different sized beakers and seeing how that constant heat that the burner was creating had very different effects on the temperature of the two beakers. So today we're going to explore why that happens. In this lesson, we're specifically going to focus on what is the difference between heat and temperature. But in the following lessons, we're going to get a little more mathematical about it. So in this lesson, I think really all you need is notes. But in the next lesson, we're going to get into the calculations. And at that point, you'll need a calculator. Okay, so if we're looking at what we saw in that last exercise, where we were heating them both up and we saw that the small beaker, its temperature rose much more rapidly than the large beaker did. Well, we need to come up with an explanation for why that was. Well, one way to view it is that the stove was providing constant heat to both of these beakers. I mean, it was pretty close to the same because the beakers were sitting on the same hot stove, and you can see they're both on the burner. So if we imagine that they're absorbing the same amount of heat, why was it that we saw a much greater change in temperature here? Well, obviously it's because there's a lot less material. But let's look at what's happening to the molecules. Well, the water molecules in both of these beakers, as that heat comes in, the water molecules start moving a little bit faster. We call this kinetic energy, right? When they start moving faster, we're going to call that kinetic energy. So here's what it would look like if we imagined we could see those molecules moving around. Now, as the heat comes in, we'd expect them to move much, much faster. Now, I wish I could get this little diagram to move faster, but it can't. But the difference between the two beakers is that the heat energy is spread out over many, many more particles here. Imagine that in the small beaker, because there's less water, let's say, now of course there's far more than 3 water molecules, but there aren't very many compared to over here. So if they're both absorbing the heat, these 3 molecules have to absorb all of that heat, and their movement is going to be much, much more dramatically impacted. They're going to gain way more kinetic energy because all 3 of those 3 have to absorb all the heat energy, whereas over here you have a lot of particles that can sort of share that burden of absorbing that heat energy. You know, one way I like to think about it is through, this metaphor. If you are giving heat to the beaker, the water molecules are absorbing that heat. It's a lot like when you give candy to kids, right? The candy is the energy, right? It's the heat energy. And the kids, well, they're like the water molecules, right? There's one water molecule, there's another water molecule, and there's another water molecule. And I don't know, maybe we'll say the mom is the stove. But in any case, that energy gets spread out over all of these water molecules. And so just like the water molecules move faster, the kids get hyper and they start moving faster too. But imagine if I gave all that candy to one single kid. That means all of this energy, is going to be going into one single water molecule or one single kid. That's like what's going on here. So that kid is going to be so hyper because of all that energy he's absorbed. Just like the 3 particles of water are going to absorb that energy, and they're going to have to move a lot faster, whereas over here, if we have 20 or 30 of them, they can kind of share that, and they don't all move quite as fast. Here's another example that is sort of going the other way, right? If we were to have 2 swimming pools, one's a lot bigger than the other one, and they were really hot. I actually think 80 degrees is a little unreasonable. I was thinking 80 degrees is probably Fahrenheit. But in Celsius, a hot pool, like if you got in it and you're like, oh, this pool's too hot, that might be more like 35 degrees Celsius. Yeah, I was thinking Fahrenheit here. But in any case, let's say they're both the same temperature. Well, one of the things we know about these 2 pools is the water particles in them they're wiggling, they have some kinetic energy, just like these do over here. And if the pools are at the same temperature, What do we know about their kinetic energy? Well, it turns out neither one of them has the highest kinetic energy. They both have to be, their particles are moving at the same rate. They have the same kinetic energy because they're at the same temperature. The temperature is what determines how fast they're moving. Now imagine we left these two pools out overnight. And over here, these water molecules, they're going to be cooling down because we've got hot water, we've got cold air at night, and we know the heat's going to leave the hot water and go to the cold air. And it will over here too, right? It's going to leave the hot water and go to the cold air while they're sitting out overnight. And you're going to walk back in, you're going to be like, ooh, this is really cold. But the question is, which pool will have the lowest temperature in the morning? Well, did you guess the small pool? Yeah, this one definitely will. This one over here might have dropped from 35 degrees Celsius. Maybe by morning it would be down to, I don't know, 21 degrees Celsius. And this one might be down to 18. It's going to get a lot colder. Well, why? Because which of these two pools has more water molecules? Definitely this one, right? This one has a lot of water molecules that are moving, and this has a lot less. These don't have to lose as much energy each. These, each one of them, because you don't have so many, are going to lose quite a bit of energy, and so it's going to cool off a lot faster. So the more water molecules you have, they can kind of share that burden, and you won't see as dramatic a change in temperature as if you had less. All right, so that's the end of this first part of this lesson before we get to the mathematical part of it, and I want you to go answer the reflective question about what we learned here.